Welcome back to 8701. So in this lecture, we talk about the Higgs mechanism. As you might know, the Higgs boson was discovered in 2012 by the LHC experiments. But the theoretical discovery of the Higgs boson happened much earlier than that. In the mid-1960s, Peter Higgs and a few others proposed a mechanism which gives rise to masses of the gauge boson, the W and the Z boson. And the Higgs boson or the Higgs field then can also be used to give masses to the fermions. So let's have a look at this and start with a simple observation. When we write down our Lagrangian for a simple spin one field, gauge field, like a photon, we find that we want to have local gauge invariance for this Lagrangian, which means that we can do a local gauge transformation of our fields, and the physics should be unchanged of this. So the physics, meaning the description by the Lagrangian, should be invariant under this transformation. All right. The problem, however, is that if you want to have a spin one gauge field which is massive, you have to have terms in your Lagrangian like this one here, where you have a mass term for your fields. So in general, this is not possible without breaking gauge invariance, and this is a guiding principle of for our Lagrangian theory. So this is a real bummer. So if you want a stopping point, so you have a beautiful theory which describes all the interactions, but one important characteristic, the masses of the particle, is missing. But you are able to actually do this not by adding a specific mass term, but by breaking the symmetry, by breaking the local gauge symmetry. And there's various ways to do this, and one of the ways is to use spontaneous symmetry breaking. So what is spontaneous symmetry breaking? Imagine you have a symmetry, a rotational symmetry like this pen here, and by applying some force on top, this pen would bend, and by bending this pen, it bends in one specific direction. That breaks the rotational symmetry. Another way to look at this is to just let this pen drop, to let it go to its ground state, lowest possible energy state, and it will land somewhere on the table. And by doing this, breaking the symmetry, and it does this spontaneously. Let's look at spontaneous symmetry breaking in a toy model first. So what we want to do here is just add a complex scalar field and a corresponding potential for this field. Potential is shown here. And this general potential can have multiple forms. So the first form would just be this parabola here. It's a solution where mu square, this term mu square, is greater than 0. In this term, there is this unique minimum. The minimum is here at 0. And because of that, the mass of this field would be equal to 0, and the mass of our gauge field would also be equal to 0. But what happens now if we have, through this potential, a breaking of the symmetry? So in this case here, the vacuum itself, the lowest energy state, breaks the symmetry. You go away from the 0 point and you're breaking the symmetry. So this minimum is at V over square root 2. V is the vacuum expectation value of this field. And you can simply rewrite then this field itself by evolving it around its minimum. And so you find two fields here, this chi and this H. The H is already kind of pointing towards the Higgs boson, and the vacuum expectation value. Now, if you add this back into your Lagrangian, and I'll do this again, this is shown here, but also on the next slide, you can start to identify terms which look like mass terms for your particle. And the first one is here, which can be identified as a mass term for our gauge field. The mass is E times V. E times V is the strength of the coupling of this gauge field, E, times the value of the vacuum expectation value. All right, so this is interesting. So we used this new scalar field to break spontaneously the symmetry, and then a mass term appears which is proportional to the strength of the coupling and the vacuum expectation value. So the mass is generated through through the spontaneous symmetry breaking and the coupling to the field. You also find a mass term for this Higgs field here, for this H field. This is not the Higgs boson, it's just a field which looks like it. And so this mass term is here, but remember that mu square is less than 0. And then this Chi, or the so-called Goldstone boson, its mass is 0. But then we have those terms left over here, which we cannot really interpret it very well. And it's possible to remove them by choosing a specific field. So we do a gauge transformation by just relabeling things. And then the new Lagrangian is independent of this field. Just as a reminder, the Goldstone boson, you find those Goldstone bosons in many places in physics. And Jeffrey Goldstone is a retired faculty at MIT. So you might, in the spring or next summer, you find him walking across the corridors. So we find our new Lagrangian, which has our mass terms here, which has a term for the Higgs field and has our potential for the Higgs field. So this specific gauge we just decided to use is the so-called unitarity gauge. And it's important to note that the Lagrangian itself contains all physical particles, but this Goldstone boson is gone. And the lingo we sometimes use here is that the Goldstone boson has been eaten by the physical bosons. And the way it has been eaten is through the longitudinal polarization of those bosons, and that's equivalent of saying that it has acquired mass. So the pocket guide here for spontaneous symmetry breaking is such that some spontaneous symmetry breaking of a U1 gauge symmetry by a non-zero vacuum expectation value of a complex scalar field results in a massive gauge boson and one real massive scalar field. So we created mass, but as a side product, we also have an additional field, and that field itself has a mass term, so it's massive. The second scalar field we had just disappeared. The Goldstone boson has been eaten by the longitudinal component of the gauge field itself. All right, that was a simplified toy model. Let's look at the standard model. So now here we have to generalize from U1 to SU2 or SUN gauge groups. The scalar field is now an n-dimensional fundamental representation of that group. For the standard model, that would be SU2. The gauge fields are n square minus 1 dimensional joint representations. Now for like our photon, for example, or our unmixed W boson field. And the Lagrangian looks very similar to the one we just before with our potential. Again, we have this mu square term. We also have a lambda term here. And then we require local gauge invariance again. Okay. So now for the standard model, again, SU2 cross U1 gauge groups, we introduce a complex field, a complex Higgs field in SU2. It's a doublet, meaning that it has 4 components. It's complex and has 2 components, which means there's a total of 4 components to it. So we already know that we want to use m square less than 0 for our potential to allow for spontaneous symmetry breaking to occur. The minimum is then at 1 over square root 2, 0 for the upper component, and V, the vacuum expectation, for the lower component. That's a choice already. Again, why mu square less than 0? Because if we would have chosen to use a positive value for mu square, we wouldn't have spontaneously broken the symmetry. Okay, so we need to have potential which looks like this Mexican head here. All right, so now we can, what happens now to our W and Z bosons? We have discussed electroweak mixing already. Good, so that was the first step. Now we will understand where the mass terms actually come from. So now we just did the did the spontaneous symmetry breaking, and now we're looking at what happens now if we also couple the Higgs field to the bosons. So again, we write this this way. And then we just try to find terms. It's really like a mechanical writing of the individual terms. And you find, again, terms which have a vacuum expectation value here and the coupling here. And you find the coupling to the U1 term and the coupling to the SU2 and the coupling to the U1 term representative to the coupling to the original photon field and our gauge field for SU2. All right, the rest is rewriting and identifying terms. If we do this, and this is like a couple of pages of writing, fine. But if we do this, we find again, like before, that we find the first and second component of our gauge SU2 gauge field gives us the charge vector boson, the W plus and the W minus. And then the Z boson and the photon are mixtures of the third component and the field B. All right. So those are our physical fields. And then we try to identify the mass terms. We find for the W that the W mass is proportional or equal to the coupling in the coupling strength of the SU2 group times the vacuum expectation value over 2. And the mass of the Z boson is given by both couplings times the square root of the sums of the squared times V over 2. Okay, if you're trying to look for a mass term for the photon, we find none, meaning that the photon is massless. And then we can look again at our weak mixing angles, and they're now defined directly through the couplings in those two gauge groups. The masses of the W and the Z bosons are related via this weak mixing angle cosine theta W. Right, those elements we already saw before. Now we find that the masses of the gauge bosons are given by spontaneous symmetry breaking via the vacuum expectation value and the strength of the coupling of the gauge field to the Higgs field. All right, so summary. We started with a complex scalar field, a representation of SU2 with 4 degrees of freedom. The Higgs vacuum expectation value breaks the symmetry spontaneously. The W plus and W minus and the Z boson acquire mass, and the 3 Goldstone bosons are each absorbed into the W's and the Z boson. We also find an additional scalar Higgs boson that remains. And so that was the study, the understanding in the 60s and 70s, and the standard model was further developed. And then it took us all the way to 2012 to actually find this new scalar particle, the Higgs boson itself.